Welcome to this lecture series in coordinate geometry. In this lecture, we'll look at a criterion to decide when two linear equations have a unique solution. And all we need to know is this fact that if we have this triangle with vertices 0, 0, PQ and RS, then the area of this triangle that we see here is given by this expression. So we had a general formula for the area of a triangle. One vertex need not be the origin, but that formula boils down to this expression when one of the vertices is the origin. Okay. Here are some problems for practice. And now let us get started. So suppose we have real numbers a and b, not both of which are 0. Then these lines, and these are lines because of this hypothesis. If both a and b were 0, then this wouldn't be a line. It would either be the empty set or the full set. So consider these two lines. Then the statement is that these two lines are parallel no matter what C and C prime are. It's a very, very simple fact. Basically, the slope of this line and the slope of the first line and the second line are the same. That's all. So if you have these two lines where C and C prime are any real numbers, then they are parallel. And if you have a line parallel to this given line, it can be written this way for some C prime. So that is something that I haven't written, but I'm sure you realize that. Okay, so now let's go to our main application. Suppose we have 6 real numbers, a, b, c, d, and alpha and beta. Then these linear equations have a unique common solution if and only if this condition is satisfied. So one can show this without any knowledge of coordinate geometry or anything, but we will look at a geometric solution. So first assume that these two equations have a unique common solution. Okay, and we want to show this and then the other direction. So I do not want to write too much. So maybe one line I will write. First assume that there is a unique common solution. To the system. And we want to show that AD minus BC is non-zero. Okay. So first note that not both of A and B are 0. Why is that? Suppose both A and B were 0, then this equation looks like 0 equals alpha. And since there is a unique common solution, there is at least one solution to this equation, which means that alpha better be 0. So this equation just treats that 0x plus 0y equals 0, and hence every point on the plane satisfies the first equation. Alright? And now the second equation has infinitely many solutions unless it has 0 solutions. The only situation when it has 0 solutions, meaning no solutions, is when both C and D are 0. Otherwise, it has infinitely many solutions. So we see that if you assume that both A and B are 0, then either you would see infinitely many common solutions to this system or no solution to this system, both of which contradict the hypothesis that they have a unique, our assumption that they have a unique common solution. So not both of A and B are 0, and similarly, not both of C and D are 0. Same argument. Alright, and therefore these are lines. Since not both of A and B are 0, the first one is a line, and therefore the second, and by the same remark, the second one is also a line. Okay, and since there is a unique common solution, these lines are not parallel. So therefore, by our assumption, the two lines are not parallel. Okay, and now what we will do is we'll consider the lines. Consider this line and this line. Okay, this one is parallel to that one, and this one is parallel to that one. But since these two are not parallel, these two are also not parallel. Alright, so these two lines are not parallel. And this passes through the point, of course, it passes through the origin. This passes through the origin, as well as it passes through the point minus b comma a. Clearly, because you can just substitute minus b and a here, and that gives you a 0. So the first line is actually this line. Okay. And the second line is similarly the line which passes through the origin and the point minus d comma c. So these are the two lines. And since they are not parallel, this triangle that we have here, maybe I'll shade it. This triangle has positive area. But what is the area of this triangle? The area of this triangle is half of absolute value of minus BC plus AD by the formula that we recalled. And since this has positive area in particular, not in particular, in fact, it's equivalent to saying that this is non-zero, which is implying that this is non-zero. In fact, that is also equivalent. So if you assume that the two equations have a unique common solution, then this necessarily happens. And now let me try to verbally say how to do the converse direction. So for the converse direction, you assume this, and we want to show that these two have a unique common solution. Okay, so once we assume this is non-zero, it automatically follows that not both of A and B are 0, and not both of D and C are 0. Okay, and therefore these two are again equations of a line. And by the same geometric area argument, we will see that these two lines are not parallel, and therefore they intersect in a unique point. And hence these two systems have a unique common solution. So the reverse is very, very similar. Okay, and I hope this was informative. One can write down a similar equation, similar condition, not equation. One can write down a similar condition for 3 linear equations to have a unique common solution. And that naturally leads to the notion of a determinant, and the same kind of area consideration, or rather volume consideration, comes about there. But let's not go into that. We are basically in this lecture series, we are only exploring the plane, not the space. Okay, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.